We continue our discussion on fracture mechanics with the topic of fatigue crack growth analysis. When do we need to employ fatigue crack growth analysis in performing failure investigation? If you are examining a component or structure that has fractured and you can establish that there is a crack present prior to the catastrophic fracture, and you can establish that the loading is monotonic, meaning that it starts from zero and it increases to cause fracture, then we need to determine if the crack length or the initial crack length would have extended under the operating load, causing the catastrophic fracture. However, if the load is fatigue and it changes with time, then we need to determine if the crack that is growing and it has reached the critical length, the maximum length to cause the fracture. This is a case where we need to introduce or use a fatigue crack growth analysis in our failure investigation. Of course, the scope of our analysis is confined to fatigue loading where the amplitude is constant. We have the maximum minus the maximum load that gives you the range, and half of the range is the amplitude. In the topic of high cycle fatigue, we look at SN curve or strength referred to the amplitude of stress versus number of cycles to failure. Now, the total life of the crack consists of primarily two stages. One is the stage for a crack to initiate, and once the crack initiates, we have another shorter stage for crack propagate. In the high cycle fatigue analysis, the crack propagation period or the number of cycles from crack initiation to the final fracture is short, and therefore we do not address the crack growth period. From fracture mechanics for monotonic loading, where the stress goes from 0 to the maximum permissible value, we have this equation for stress intensity factor, where y is the geometry factor. Now we are considering fatigue loading, where the stress here will make a sinusoidal cycles. Now we are going to apply the stress intensity factor value at the maximum stress level. So we have K1 maximum will be equal to sigma maximum multiplied by this term here. And again, we apply the same equation, which is valid for the minimum or at the minimum load level, where we have K1 minimum is equal to sigma minimum multiplied by this term. So if we now consider the maximum K1 minus the minimum K1, we would have delta K1. Delta will mean that the range of K. And we have that, therefore, we have sigma maximum minus sigma minimum, which gives us delta sigma multiplied by square root of pi a and also the geometry factor. Now, while K1 is referred to as the stress intensity factor, delta K1 is called stress intensity factor range, and that is applied for fatigue loading. The subscript 1 only refers to mode 1, where the crack is going to propagate perpendicular to the applied stress, and therefore this is considered as the opening mode of the crack. Now we want to introduce the term fatigue crack growth rate, or dA over dN. Consider a crack under mode 1 loading and the crack is propagating under these load cycles. We can monitor how fast the crack is growing, that is A, as a function of the applied number of cycles, and this is typically how the curve would look like experimentally from measurement. Now, if we take at any point of the curve, we can determine the slope of this curve, and that would give us delta A over delta N. And at this point now, in the limit that this goes to 1 point, we can get dA over dN. And the average of this point here will provide us the crack length. And the crack length now will go into the stress intensity factor range equation, and that would provide a pair of data that is dA over dN versus delta K. Now, this pair of data along this curve now would provide for us the fatigue crack growth rate curves that will be examined next. This is a schematic for a fatigue crack growth rate curve. We plot dA over dN in log-log scale, so we have the units A in millimeter or in meter per cycle. That's the crack growth rate per cycle in a log-log scale. Now, the curve can be divided into three regions. Okay? The first region here is referred to as the threshold. Threshold is the limit. Delta K threshold is the value of delta K below which the crack will not grow. That is referred to as the delta K threshold for the material. Now, the second region is represented by a straight line, and this straight line could be written in the form of a power law because the data is plotted in the log-log scale. So as a power law now, we have two unknowns. We have C and also the coefficient and also the exponent M. Now this equation is valid only for the second region and is referred to as Paris equation. And finally, we have the crack acceleration where the slope is increasing, reaching to the final fracture of the materials. And the final fracture is bound by the value of delta K approaching fracture toughness of the material. If there is no indication on the plot of fatigue crack growth rate curve, we should look for the R ratio, and commonly the R ratio used is R is equal to 0, which means that now the load cycle has a minimum of 0 and maximum of a positive value. When we examine the fracture surface of a component, we can look for a few distinct features. Here we show the typical morphology. There is a condition of fracture surface where we are looking normal to it and the loading is in the direction out of this plane. Now there are three different features, distinct features that we can see here. First is the faceted planes. These are planes that is more like indicative of a brittle fracture here. A very clean plane that we can see. This is the surface where crack is propagating from left to right. However, oftentimes we can also see cracks or traces of the cracks in the direction normal to this screen. So that is referred to as secondary cracks. The other thing for fatigue, we can identify at proper magnification fatigue striation that is provided or shown as the parallel, very finely spaced parallel lines here, and that is indicative of fatigue crack propagation. And it has been shown in some research that the space between each of these striation lines would represent the crack propagating for one load cycles. And what we see here is described as the growth mechanisms of the crack, and in failure analysis it is often used as a confirmation for our mechanic calculation that cracks propagated under fatigue loading.